The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
All right, our next speaker is Dr. Zhang. Dr. Zhang is a commercial building energy analysis at PNNL, which is the Pacific Northwest National Laboratory. He has worked on development of ASHRAE standards 90.1 and 90.2 and, 90.1 and 189.1. ASHRAE Advanced Energy Design Guides and Advanced Energy Retrofit Guides, and other high-performance building projects. He has an extensive experience in computer modeling for commercial building energy performance. He is also a consultant of ASHRAE Standard Project Committee 189.1. Before joining PNNL, he has received his PhD degree in building engineering from Concordia University in Canada in 2009. During his graduate studies, he has been a key contributor to the integrated environmentally response elements in buildings and moisture control for external wall system projects, Annex 44 IEA ECBCS. Please help me welcome Dr. Zhang.
Good afternoon, ladies and gentlemen. Thanks for staying for this session. Yes, I'm from Pacific Northwest National Laboratory, and most of our work is under Department of Energy, the Office of Energy Efficiency and Renewable Energy. At the beginning, when I look at the titles, State of the Art, I wanted to cover a brief introduction about the history of building modeling software, but since Jeff has already done that, and you have heard from him that the softwares are really started from maybe 1970s. At that time, I was just born, so I didn't feel comfortable to cover the history. But instead, I would like to share some experience from user perspective. Because at PNNL, we have a group of around 20 people using EnergyPlus, which is one of the simulation software on a daily basis. And we review each other's work, and some members of us are also developers of the software tools. So we have some experience, and I'd like to share with you here. So the outline of today's presentation, I want to narrow down the topic of building modeling a little bit. I'm going to specifically talk about the building energy simulation, not other applications. And also I will cover what's the performance criteria that limit what building energy simulation software can do for us. And since this group of audience is interested in thermal mass, I will talk a little bit about the modeling method in EnergyPlus for heat conduction. Also some applications, most of them are PNNL project for Department of Energy, including support for ASHRAE standard 90.1 code development. So talking about the scope, Department of Energy maintain a tool directory which include more than 400 software tools. They categorize these tools into different subjects. And building energy simulation is only one subset of these simulation analysis tools. So what building energy simulation do for us? It requires you to, from a user perspective, it requires you to input building design characteristics, the schedules, the occupancy behavior, and also it requires you to input the climate data. And after the calculation, the output of the software is the whole building energy use. And a lot of other information, for example, the zone temperature, whether the load has been met or not, and the energy use by day, by hourly information, and also total, annual energy use. So what can we do with energy simulation? What's the use of it? We can use it to evaluate the energy efficiency measures, EEMs. Let's say you have a particular building design and you want to alter it a little bit, and you want to say, for example, change the window-to-wall ratio or increase the insulation. What's benefit I can get? You can use energy simulation to build a model for your original design idea, and then model another building, which is the alteration of that building, and look at the energy difference. That tells you how much energy you can save or lose by doing this alteration. And then if you put your cost in it, then you can calculate the life cycle cost, whether this is the cost-effective investment for doing that. The other application is to show design compliance. As Steve has just mentioned, that ASHRAE standard 90.1 is a baseline building code, meaning that any state adopt this code will build the building at least meet the minimum requirement of 90.1 standard. However, most of the standard is written in a prescriptive way, so you have to meet everything. But designer can have a flexibility to change it a little bit. For example, if my insulation value or window-to-wall ratio do not meet the 90.1 prescriptive requirement, then I can choose to use energy cost budget path to show my compliance and get the building permit. This is the principle, and the principle is built on that you model a building which is happen to meet the minimum requirement of 90.1 in prescriptive provisions. And then you model your design building. If your design building costs less energy annually than the baseline building, then you still show your proof that you comply with the 90.1. And third application is very common. A lot of consultant companies are doing the work, getting business for show high performance. Building have a high performance in terms of energy use. So it's a similar concept as the energy cost budget. It has other limitations or requirements in using this way. But the principle is that you have a baseline building which meets 90.1, and then you have a proposed building. The energy difference divided by the baseline building energy use tells you how much better is your proposed building than a code minimum baseline building. And then with that percentage, you can get LEED credit for your high performance building. Last but not least, we can use energy simulation to, as an experimental tool to test some different research, for example, study HVAC control or daylighting and other applications. So I referenced the performance criteria from 90.1 Appendix G to say what building energy simulation that I'm talking about, what needed to be. So the criteria include that you have to be able to model hourly, the building performance hourly in a year, and to reflect the hourly variation in occupancy, thermostat control, and your operation of your HVAC system. And specifically, it also requires you be able to this software be able to model thermal mass effect and have more than 10 thermal zones capable of modeling more than 10 thermal zones and other requirements. And the last one has been mentioned in previous presentations that the ASHRAE standard 140 is a standard that to qualify building energy programs so that they at least can ensure some confidence in your simulation result when you use it. So I borrow from USGBC's Advanced Energy Modeling for LEED technical manual that it provides a list of software programs that qualified for LEED application. So, but this is not; these are not the complete list. It's just example files. And I'm primarily in our lab we use EnergyPlus as a tool. It's a free software funded by the Department of Energy. Sometimes practitioners can consider it as a research tool because the user interface hasn't been developed so well, and so sometimes it takes time to define the input. So I'll use an example in EnergyPlus to show that how what's the options that you can use to model heat conduction. The transfer function method mentioned by Professor Haber was mentioned by him. So the transfer function is an algorithm that you consider the heat flux through a surface of an element can be calculated based on the history of the surface flux at this surface and the temperature history at this surface. And also the CTF transfer function coefficient of the element is also in this equation. This is just a simple idea. And then the thermal mass is counted within this. The material property is calculated to calculate this CTF coefficient. So, and more advanced method, this CTF method is a default method, is the most simplest method in EnergyPlus. If you want to go more advanced method, you can go to use a finite difference solution algorithm, which you discretize material in one-dimensional, and you solve the temperature at each discretized domain, and you get temperature. This is particularly useful when you analyze, for example, phase-changing material. If your material property, conductivity, the density, and other parameters change with temperature, then you should use this method. And even more advanced method can model heat and moisture transfer, but this method usually costs more computational time, and also the user has to input a lot of more information to describe your material. So back to the default method, the basic input from user, you need to define your material. Material requires you the thickness of material, the density, conductivity, and specific heat capacity. Once you define your multiple materials, you can compose them to become a wall assembly. And this is just an example that the first layer is a concrete panel, second layer is a cavity insulation, and the third layer is a gypsum board. I want to mention that in the second layer, which is actually have a two-dimensional or even three-dimensional heat transfer. But in current simulation software, all the heat conduction is considered as one-dimensional. So that when you input the thermal property of the second layer material, you have to consider what's the effective thermal resistance or conductivity, what's the effective density. Then you will be able to capture the property of that layer. So now I'm going to turn to some example that at our lab we use energy simulation to do research. First example is a retrofit project that we help a large retail store to retrofit their 1987 building at Virginia. And the objective of doing this energy simulation is first to calibrate our energy simulation based on the known operation schedule occupancy information. We know the historical energy use, the utility bill of the building, and we also want to conduct some energy audit. After get this model calibrated, we can use it to evaluate the potential energy saving and impact of different retrofit measures. So without going to details, I'm just showing the result, what energy simulation can tell you. On the left side is this is the energy use index, the kBTU per square foot per year. And on the right column, you can see the energy, accumulative energy savings in annual base. And the different color represent the different energy use. So first we calibrated that building based on the, their utility history and building characteristics, build that model. And then we started to add different EEM component to that building model and see how much energy does it save. This chart shows accumulative measures from so it means that if you add all the EEMs together, we achieved 48% of energy saving compared to the current stage. And also, this is the cost saving curve. When the owner or the designer gets this information, he can evaluate the different investment scenarios and make decisions. The second example I'm going to mention is a project under ASHRAE Advanced Energy Design Guide development. We looked at the new construction for quick service restaurant. This is the schematic of the building. It's quite small building, just with 2 zones and one plenum. This is not the actual building design, but we want to use the simulation to develop climate-specific package, advanced energy design package, which include HVAC, the lighting envelope, and all aspects of building. Try to save energy to 50%. So it's related to design for different climate locations. And the result shown here, again on the left, is building energy, annual energy use, and the different color shows the energy use. For each climate, we modeled the same building prototype for 17 climate locations, and each location may have different design package depending on their actual climate information. And then we reach 50% energy goal for 2 cold climate locations. And others we were able to achieve over 40%. The fact that we were not able to reach 50%, one of the reasons is that restaurant, especially the quick service restaurant, has a lot of energy use for appliance, their cooking appliance. So that those we don't have much measure to control or regulate those. The third example I'm going to want to mention is some work that PNNL helped ASHRAE standard 91.1 on their continuous maintenance process. ASHRAE standard 91.1 is keep evolving and periodically republish their standard by including different new requirements, and it's towards a more energy efficient way. So before 91, 2010 was published, the standard committee and DOE had the goal that they target energy saving in national wide to reach 30% energy saving and energy cost saving. So when the committee, Standard 90.1 committee worked very hard to improve their requirements, we wanted to measure how much progress they have gotten. And for each added addendum, new requirement to it, how much energy gain we can receive. So that's the goal of the project. And what we did in the methodology is to build a baseline model based on 90.1 2004 prescriptive requirements. And the other model, or the other suite of model to represent is by the requirement, new requirement to be written in the 90.1 2010. So in order to be able to cover all building prototype and all climate locations, National Renewable Energy Lab and PNNL together develop a suite of building energy models. We call it prototype building models. They cover different size of office, size of different type of retail, restaurant, healthcare building, hotel, apartment building, and by a survey for the recent new construction for different climate locations, we conclude that these prototype buildings covers 80% of building U.S. new building stock. And in order to represent different climate locations, we model those buildings, each of building in 17 climate locations. This is the overall of the building simulation results. So you have to consider to create this graph, we have to model 16 prototype buildings. Each of them have 2 standards. And for all of them, we have to model for 17 climate locations. So that's a lot of building simulations together, and then we have to post-process the simulation result in order to get the national weighted average. So on the horizontal line, you see different building prototypes, and the last one, highlighted one, is the national weighted average difference between 90.1 2004 and final published 90.1 2010. Here you look at around the 25.5% of energy saving, but the goal of 90.1 2010 was energy cost saving. So we have to consider the cost for therms and electricity, and then we also consider that since 90.1 do not regulate some of plug load, for example, your appliance, then we take that took those out of the denominator, and then we were able to claim that 9.1 2010 achieved its goal of 30% energy cost saving. So this is just some link to our work for this code development 9.1 models. We not only provide the report how its work can perform, we also share with the public domain about our simulation models. So all the EnergyPlus simulation models are available, and their description is available on our website. So in summary, that energy simulation program are tools to help us to evaluate EMs. It can be used to show code compliance or performance rating of a building. We also can use them for research different ideas. We have the community has created a performance criteria and even a standard 140 to ensure the confidence of simulation result once the program has been approved by using that test method. And the current program can account for thermal mass and even moisture transfer through building envelope, but they require more computation time and detailed information, which is probably not available for every modelers. So this is the limitation that currently we have and the world that we live. Lastly, I mentioned that from the example I've shown you, it's proof that the building energy simulation program are used to make important investment decisions for building energy design, building energy retrofits, and even the building energy code that put our future building at minimum energy efficiency. We also use the energy simulation to develop them and to quantify the saving of it. That's my presentation. Any questions?